Physiology SAQ19 Hemoglobin. A. Describe the structure of adult and fetal hemoglobin. Adult hemoglobin consists of HbA1 and HbA2. HbA1 exists as a tetramer containing 2 alpha and 2 beta polypeptide globin chain subunits, where alpha chains are shorter than beta chains. HbA1 makes up of 95 to 98% of hemoglobin in adults. Each subunit contains a heme group that diatomic oxygen molecules can bind to. The heme moiety is formed of an organic protoporphyrin ring and a central iron ion in the ferrous state, Fe2+. The heme group is attached to a histidine group on the globin protein at a constant distance from the end on the globin chain to form one subunit of hemoglobin. HbA2 is a less common adult form of hemoglobin that comprises of 2 alpha and 2 delta globin subunits and makes up 1 to 3% of hemoglobin in adults. Fetal hemoglobin, HbF, is an alpha-2, gamma-2 tetramer, and while having exactly the same alpha chains as HbA. Each subunit contains a heme group with an iron element, which is key in allowing binding and unbinding of oxygen. 2 gamma polypeptide subunits are highly homologous with HbA beta chains, but with significant structural differences, causing deoxy-HbF to bind less tightly to 2,3-DPG compared to deoxy-HbA. As a consequence of the structural differences between these two isoforms of hemoglobin, HbF exhibits a higher average affinity for oxygen than HbA. Histidine in HbA is positively charged, hence binds with negatively charged 2,3-DPG. HbF has serine instead of histidine at position 143 on globin chain. Serine is neutrally charged, hence minimally interacts with 2,3-DPG. Hence HbF has low affinity for 2,3-DPG, causing HbF to have higher oxygen affinity than HbA, leading to left shift of OH-DC curve. P50 of HbF is 19 mmHg compared to P50 of HbA of 26 mmHg. B. Describe the molecular mechanisms of oxygen binding by hemoglobin. Oxygen binds to the ferrous ion by forming a reversible bond at the bottom of the crevice in the globin chain, formed by electrostatic bonds in the molecule. There is no oxidative reaction, so the ion atom is always in the ferrous form, Fe2+. Hemoglobin can exist in two structural forms, the tense T form and the relaxed R form. The difference between the two forms is brought about by a slight rotation of one pair of subunits with respect to another. In deoxygenated Hb, the bonds are strong and Hb is in its tense form. As each oxygen molecule binds, the bonds become weaker and hemoglobin takes on its relaxed form. The crevice opens and oxygen binds more easily until 4 oxygen molecules have been bound, at which the hemoglobin is saturated. This gives rise to the sigmoid shape of the oxygen-hemoglobin dissociation curve. This phenomenon is positive cooperativity. Oxygen binds about 70 times more easily to heme in the relaxed form than in the tense form. One heme group can bind reversibly to one molecule of oxygen. Hence, each hemoglobin molecule can bind to 4 oxygen molecules. The conformation of hemoglobin molecule is altered by physical and chemical factors, such as temperature, hydrogen ion concentration, CO2 concentration, and 2,3-DPG concentration, thus changing the affinity of hemoglobin for oxygen. C. What abnormal types of hemoglobin may exist in humans and how do they differ? This includes thalassemia, HBS, methemoglobin, and carboxyhemoglobin. Thalassemia is an inherited autosomal recessive blood disorder in which the genetic defect results in suppressed alpha or beta chain production, leading to excess HbF and left shift of the OH-DC curve. In sickle cell anemia, a genetic defect on chromosome 11 results in the replacement of glutamic acid by valine at the 6th residue in the beta chain, causing hemoglobin to polymerize at low PO2, also known as sickling. Thalassemia is a quantitative problem where too few globin chains are synthesized, whereas sickle cell anemia is a qualitative problem with the synthesis of an incorrectly functioning globin chain. Sickle cell anemia is inherited in an autosomal recessive manner. The heterozygous state confers an advantage against malaria as the shortened lifespan of erythrocyte prevents the blood-borne phase of the mosquito from completing its life cycle. In the homozygous state, the abnormal hemoglobin is susceptible to forming solid, non-pliable sickle-like structures when exposed to low PaO2, causing erythrocytes to obstruct the microcirculation, leading to painful crisis and infarcts. Methemoglobin. Iron in heme in methemoglobin is oxidized from the ferrous state to the ferric state, Fe3+, which can't bind to oxygen, and as a result methemoglobin cannot deliver oxygen to tissues. Deficiency of the enzyme methemoglobin reductase, which converts ferric ions to the ferrous state, or some drugs such as the metabolite of prilocaine, or toluidine, can increase the amount of methemoglobin and impair oxygen carriage in the blood. Carboxyhemoglobin. This is formed when carbon monoxide binds to hemoglobin instead of oxygen. Carbon monoxide has 200 times greater affinity for hemoglobin than oxygen. Increased carboxyhemoglobin shifts the OH-DC curve to the left, resulting in impaired oxygen delivery at the tissue level.